Good morning, and thanks for coming to this presentation about a lightweight typing assistant for fonts. Fonts is an iOS and Android app built by Bending Spoons that essentially lets users type using Unicode fonts. Building your own keyboard essentially has an additional requirement, which is the one of having to create your own typing assistant. And by typing assistant, we mean a system that essentially gives support to the users while typing by providing features, for example, like autocorrection, next word prediction, and suggestions of word completions. One big issue in this, one big challenge in this situation is that off-the-shelf solutions are not available. And this is because mobile keyboard developers, such as Google with their Gboard, Apple for the iOS keyboard, and SwiftKey, they use their typing assistants as a competitive advantage to compete with each other. So they don't release any code open source. So the main challenges, actually two of the main challenges that I want to outline here about building your own typing assistant is, first of all, the typing assistant needs to be real time. And this is because the users are expecting your support and to receive compelling suggestions shown on the keyboard to be available after every single keystroke. And studies have shown that the average typing speed on mobile devices has been estimated roughly around 300 milliseconds per keystroke, or 3 keystrokes per second, roughly. Given this limited time frame that we have, we need to use an on-device solution, and we're not able to use any remote API. The second big challenge that we need to tackle is the fact that we have very heavy constraints on the resource that we have available. And this is because essentially, since the keyboard is running on top of another app, let it be WhatsApp, Instagram, or Notes, for example, most of the resources, actually all of the resources are assigned to the host app. The keyboard ends up having very limited resources, both in terms of computational resources and of memory. And additionally, keyboards are not allowed to use accelerators. So now let's try and go over the inference pipeline for autocorrection, for example, to understand how this system is built and how it works. So let's take for this example a sentence that a user has typed, which is "the cat is on the tab key." So first of all, what we need to do is we need to understand which words do we want to consider as correction candidates. Ideally, we could use the entire English vocabulary, but you can easily see how that is not going to scale. And also, almost every single word in the vocabulary is not going to be relevant in this case to correct the word tab key. So the first system that we encounter in this pipeline is the candidate generation model that essentially tries to narrow down the number of potential candidates that we want to consider. In the iOS version of fonts, for this typing assistant, we use an Apple on-device SDK, which is called UI Text Checker. And let's assume, for the sake of this example, that given the sentence "the cat is on the tab key," the correction candidates that are going to be produced by UI Text Checker are two, which are table and take. Now that we have these two correction candidates, we need to understand which is the best one. And first of all, we go through a round of feature engineering. So a good correction essentially has two requirements, which are: the first one is the fact that a good correction makes sense in the reference context, so with the other words that have been typed in that sentence in the given language, of course. And the second requirement is the fact that it needs to be somewhat similar to what the user already had typed originally. So the language model is the system in this feature engineering pipeline that essentially answers the question, how much sense does a word make in the language that we're typing in? And what we use in this case are n-grams. So we use a frequency-based approach for which we assume that the more frequently a group of words are used together in the language, the more sense they make. So. And this is why we use essentially this n-gram approach. The error model, on the other hand, essentially tries to answer the question of how likely it is that the user wanted to write table originally, but essentially ended up writing tab key by mistake. And what we do is we compute the edit distance between the candidate and the original word typed by the user. And then we weight this edit distance by the information about how keys are laid down on the QWERTY layout. And this is because generally when users type one letter instead of another one, they generally type surrounding keys to the one that they wanted to type originally. So now that we've gone through this feature engineering process, what we have are two feature vectors, one for the candidate table and one for the candidate take. The third system of this inference pipeline is the candidate scoring model, which essentially takes a feature vector of a given candidate and gives us a quality score between 0 and 100%. We use a random forest for this system, and let's assume, for the sake of this example, that the candidate scoring model returns a score of 73% for the candidate table and a score of 13% for the candidate take. Now, what is shown to the user is a table is shown highlighted in blue on the suggestions bar because it's the best candidate and it's gonna be used for autocorrection. While take is a weak candidate, and we're still gonna show it on the suggestions bar, but not highlighted in blue in this case. So that if the user wanted to actually type take, they can just tap on that suggestion. So given this information about the inference pipeline for autocorrections, we just want to mention some other additional features that are present in the typing assistant of fonts. So one important feature is that we are able to score also the contextual fitness of the word that the user had typed originally. And this is because we use it for autocorrection to determine whether it should be autocorrected or not. Because essentially, if the user by mistake ends up typing a word that exists in the dictionary, in the English vocabulary, we need to understand whether like the user actually wanted to type that word, or if in the context it doesn't make much sense and we have a better correction candidate available, we're gonna apply an autocorrection. Then other two features that I need to mention are the fact that we have trained the inference pipeline also to produce and score word completion suggestions, which are essentially replacement candidates that have many more letters than those typed by the user. And next word predictions are essentially candidates that are shown to the users when they're about to start typing the next word. Now, I just want to give you some results that were recorded live on users using the Fonts Typing Assistant. And on average, we've recorded roughly 23 million monthly automatic corrections applied, and these have been applied with a precision of 87%. Whereby precision, we mean the fact that a user, that an autocorrection is applied and the user doesn't edit the word that has been written by the autocorrection. And together with these results, we've also recorded roughly 3 million monthly suggestion bar usages, so suggestions tapped from the suggestions bar. Future work that has been planned for this system is, first of all, the possibility of having some on-device personalization of the typing assistant behavior, and this is because every single user has a slightly different way of communicating. They use different typing habits. They make different kind of mistakes when they type. So we want to be able to actually learn the typing habits of the individual users on device, and to perform better autocorrections and show more compelling suggestions. Then we want to add support for other languages, because at the moment the typing assistant for fonts is English only. And then we want to be able to suggest also some of the content that is present in the keyboard. So for example, fonts, but also emojis and camojis. Thank you for your attention, and I hope you're having a great day at Synapse.